I just noticed that I did the last podcast without wearing the headphones, but it was lying right here. The sound seems okay, so uh, thank goodness for that. Anyways, moving more on red tides. So you can see this is an example of a red tide. They can be pretty big and can be easily seen from satellites as well. They can happen in natural conditions, as I said before. During certain seasons off of Benguela, for example, you get huge harmful algal blooms because the upwelling is so strong, and you get miles and miles of fish kill on the beaches. Okay, it's a natural phenomenon that happens, and we'll see why the fish die. Sometimes it is related to anoxia, sometimes it's related to shellfish, the toxins from the harmful algal blooms, and so on and so forth. So some produce toxins that are inadvertently consumed by the fish and shellfish because they don't know. They just find food and they eat it. And then we'll see again the idea of bioaccumulation, where the fish and the shellfish are eaten by other upper trophic level species like seals or birds, and they can get poisoned as well. And there's a very cute example of that we will see. Okay, so humans eat affected fish without knowing, and you might end up with things like paralytic shellfish poisoning, where you feel temporary paralysis from the poison from the fish, the toxin from the fish. Typically not dangerous, but it can be. There are cases where people have been seriously injured or even dead. So most places there is a season during which the predictably the phenomenon of harmful algal blooms and toxins in the seafood happens, and dinoflagellates are associated with another kind of seafood poisoning called ciguatera. This is also something that humans don't want to go through, right? So here you are looking at the flow chart of the things. So that toxins are produced from the red tide right here. They are consumed by the zooplankton, which eat the dinoflagellate, and then the fish eat the zooplankton. The fish are eaten, then can give it to their fish larvae. They reproduce, or they can give it to the microbial food web, which means they can die and get remineralized and continue to pass the poison to things that filter the water and consume all the particulate matter, like clams and mussels and scallops. They just sit there and they keep filtering water, and they accumulate the particles as their food, which means they're accumulating poison. And human beings can end up, of course, the bivalves and so on are eaten by crabs and whelks and drills and so on, and humans can eat crabs and clams and so on, right? So human beings can also directly eat the fish, and seabirds end up eating the poisoned fish as well. So you can see that there is a complex way in which the microscopic algae that produce the toxin as harmful algal blooms can end up putting it throughout the system. And there are relations to temperature, upwelling strength, and so on, which means there is a relation to global warming, right? And its impact on the ocean warming. That kind of transitions us to another condition in the ocean that can favor harmful algal blooms. When we say harmful, we measure it by our standards, right? But there are also seals which can die, and birds get affected by this as well. So another condition that favors the competitive nature of these blooms as opposed to other photosynthetic algae is eutrophication. We said eutrophic and oligotrophic to refer to productive regions and ocean deserts. Here eutrophication means it's an artificial enrichment of waters in a region where there was previously scarce nutrients. Okay, this can typically cause harmful algal blooms, and these are the nutrient concentrations are increased by sewage, which hasn't removed all the nutrients like nitrates, phosphorus, iron, whatever else in it. fertilizers, which are high in phosphorus and nitrogen, and animal waste. There are lots of cattle and chicken farms that are industrial scale, and they produce concentrated feces, animal waste that can get washed into the groundwater, into the ocean, or into the local stream, and then into the ocean. Okay, how does it work? Basically, if you have excess nutrients, then there is a huge bloom, and whenever there is excess nutrients, there's a competition, and the harmful algal blooms may end up winning the competition. The bloom is so large that the phytoplankton will, the zooplankton will not respond as quickly, so the algae are not ingested, digested, so they just sink. You can see here the river water can bring lots of nutrients, so you have some saltwater fish, then you have a huge algae bloom because let's say there is a monsoon, lots of nutrients are getting washed into the river, into the ocean, unlike the pre-monsoon season. Okay, then those algae not consumed in time and sink to the bottom, and there are microbes which are going to respire this algae, right? So then what do? Every time somebody consumes something, every heterotrophic species is going to use up oxygen, right? So they this is a big buffet of phytoplankton coming down, organic matter, and they're going to really bloom. The microbes themselves are going to bloom in response, and they're going to respire all this hydrocarbon and use up the oxygen. The oxygen is going to drop below 5 ppm, which is needed, or which becomes hypoxic, or can also drop below 2 ppm, which then becomes anoxic and can suffocate the bottom dwellers. Those who can move can obviously move away, but not all the species, like crabs, whelks, drills, etc. cannot move, right? They just can run a little bit. Okay, so what's happening to the dead zones? These are called dead zones. Naturally speaking, the Baltic Sea has the largest dead zone every year. Mississippi Delta has the second largest, but you get naturally occurring anoxic regions in the Arabian Sea and Bay of Bengal and so on. So with human activity on land, with changing rainfall patterns, with urbanization, agricultural practices and so on, more nutrients getting washed up, runoff increasing because of urbanization, all the drip of the oil and so on washing in. So since the 1960s, now there are more than 500 eutrophic regions with dead zones, and you can see these spots here, a lot of them along the US Gulf Coast, East Coast, and Europe, China, Japan, and so on. So the scales are showing here particulate organic matter and population density of the human beings on land, as well as the dead zones. Okay, so a lot of information there that you can stare at. So Gulf of Mexico is a classic dead zone that's discussed a lot. As you can imagine, all these regions would have been forests before colonization happened and urbanization, and this is the bread basket of India, which means of the US, which means huge agricultural activities. And if you deforest and build agriculture, any rain that falls is going to wash off into the rivers, streams that combine together into the Mississippi, and the Mississippi is going to make it all the way down into the Gulf of Mexico. Warm waters also favor high metabolic rates. So you have 22,000 square kilometer of hypoxic zone, and there is some evidence that actually it's increasing in size. So dead zones, anoxia and hypoxia are a serious problem now around the world, and something that have to be monitored. There are lots of regulations being made to control what is being put into the water, either from the agricultural land or from urban wastewater, urban runoff, and so on. But nonetheless, population increases, human activity increases, land use change happens, deforestation happens, runoff increases because extreme events or rain is falling not very lightly anymore. It comes as heavy rain, which means it runs off quickly and takes nutrients with it.